Going back to a couple of days ago when we started talking about Kepler's law, I had some notes that were in there that I said we haven't gone through enough stuff to be able to get to those ideas. We're going to go through that today. So what I did is I just copy and pasted all the information of the notes that we did not get a chance to go through. I just copy and pasted there so you don't have to go back and find on your old notes where we didn't go through that. Kepler's third law is analysis of planetary motion by Kepler. What he came down to was each planet travels on an elliptical orbit around the sun. The sun is the focal point of the ellipses. Imaginary line can be drawn from the sun to any planet, smooths out equal areas in equal time intervals. The square of the planet's orbital period, t squared, is proportional to the cube of the average distance, r cubed, between the planet and the sun. T squared is proportional to r cubed. What we noticed, though, is the idea that Newton's used Kepler's law to support his law of gravitation. What keeps an orbit nearly circular motion? Well, that is the centripetal force. Okay, even though there is not a rope tied to every planet going around the sun and keeping in the circular motion, we still have a centripetal force there. We don't have this rope. We don't have this rope that's tied to every planet that keeps it going around in a circle. Okay, we don't have that. But what we do is we have a force of gravity that allows our planets to stay in the same motion, okay, or a circular motion around the planet. Going through some of the ideas that are some variables that we have talked about. T is the period of revolution, the orbital period. 2 pi r is the circumference of the distance of a revolution going around the sun. R is the radius of the orbit. Mass 2 is the mass of the object that's being orbited, and MO is the mass of just an object. So the Earth would be the mass of the object going around the sun. Okay, M2 would be the sun. The moon going around the Earth. Okay, the Earth is now being orbited, so mass of the object is the moon. So whatever is orbiting, the object that is orbiting is the mass of the object. The M2 here is the mass that's being orbited. That's the mass that's being orbited, that's going around. The MO is the mass of the object that is orbiting. Okay, the orbiting object. Okay, so there's 2 different objects: the object that doing the motion and the person that, or the object that is just stationary. We also have our tangential velocity. Our tangential velocity, which we calculated before, was 2 pi, which is just 2 pi r, which is just your circumference. This is just the circumference of the orbit. That's the circumference of the orbit. And the t is the amount of time it takes. So your distance that you're traveling divided by time is your speed. Going back to our basic philosophy of what is speed? Displacement, or distance traveled divided by time. This force of gravity is the centripetal force. Okay, the force of gravity is the centripetal force. The gravity is what keeps the planets going in a circular motion or nearly circular motion. And what we talked about yesterday, this gravitational force is equal to the product of the 2 masses divided by the distance between the 2 masses, the radius squared. Okay, the product of the 2 masses and the distance of the radius squared. So if we had 2 masses here, okay, and this is going around the other mass, We have mass of the object. Here's my mass of the object. Here is my M2. The mass is being orbited. We have a distance, which is your radius from the two centers. What I'm trying to do is just once again get a picture down there so you can sort of see what's happening here to explain the terms. The amount of time it takes to go all the way around is t. So when I travel all the way around here, this time is equal to t, going in this orbit. And then we calculate our centripetal force. This is our centripetal force, is mass times acceleration. This is my centripetal acceleration. My centripetal acceleration is v or tangential velocity squared divided by my radius. This is what we talked about last week. This force of gravity is the force that keeps us going in a circular path. Okay, the force of gravity keeps us going in a circular path. So the force of gravity that we talked about yesterday and the centripetal force, which we talked about last week, they have to be equal. Well, let's see what happens when these two things are equal. Well, I have mass of the object and mass of the object on both sides. What will happen is these will cancel out. You have a radius and the radius squared on the bottom. One of the radii will cancel out. So what we are left with our equation, with the equation is we have gm2 divided by r is equal to this tangential velocity squared. Now, if we take a look at this tangential velocity is equal to 2 pi r divided by t. So this gm2 divided by r has to equal 2 pi r divided by t squared. Once again, we're just substituting in our tangential velocity. Which will give us gm2 divided by r is equal to, distributing to all of our terms here, we have 4 pi squared r squared divided by t squared. Just distributing our exponent of 2 to each of the terms. 2 squared is 4, pi squared, radius squared is equal to t squared. So if we look at our equation, I'm going to multiply both sides by t squared, and I'm going to multiply both sides by r to get rid of our bottoms. So what we're left with here you're multiplying both sides by r. That will cancel out my r's. This will cancel out my t squareds. I'm just trying to clean this up a little bit here. What that will leave us is it will leave us with t squared gm2 is equal to 4 pi squared r cubed. Oopsie. That's by multiplying both sides by r and by t squared. Dividing both sides by gm2. What this ends up being is t squared is equal to 4 pi squared gm2 r cubed. The 4, the pi, the g, and the m's, these are all constants. These are all constant. So what we have is we have t squared is equal to some constant times r cubed. Which now if we take a look at our third law from up above, the Kepler's law. The square of the planet's orbital period, t squared, is proportional to the cube of the average distance, r cubed, between the planets, which we just showed right here. When we have something equal to a constant times something else, these are directly proportional. So it supports the idea that Kepler's idea from up above that the period squared is proportional to the average radius cubed. So we have, and if we simplify this, if we take the square root of both sides, what we're left with is t is equal to our 2 pi, we can take the square root of that, 2 pi times the square root of r cubed divided by gm2, which is what we have right here. Just taking the square root of both sides. So the orbital period is equal to 2 pi times the average radius times divided by g times the mass of what is being orbited. Weight is the downward force of mass. We have a mass here, this pen. Okay? The weight is that downward force of that mass. When you step on a scale, you weigh the downward force of your mass. A scale measures the downward force of a mass. So that a scale measures the downward force of a mass. Newton's third law, every force there is an equal but opposite force. A normal force is pushing upwards. Newton's third law, equal but opposite. You run long enough, whether it's on the track, on the basketball court, especially when you initially start, your knees will ache a little bit. They will ache. Well, why is that? Well, you are running. That floor is exerting a force back up onto your legs and your body. And you're feeling it in your knees. Your knees are like shock absorbers. And everything in there and the muscles that you feel in there, they're shock absorbers for what is occurring underneath you. Just like when you go down the road and you hit a bump or a pothole, you have shock absorbers. You don't feel much as a driver. You'll feel a little bit of jolt, but your car feels a lot. If you're standing in an elevator and in a stationary with a scale, your normal weight is measured. You're standing there on the scale, you step on the scale, you measure your weight. That is your weight. What happens if the elevator is going down on a free fall and you step on the scale? What do you think happens to your weight? Yeah, much less. Why? Because there is no force pushing back upwards. If there's no force pushing back upwards and you're just dropping, you don't weigh much. So if your elevator is in a free fall, you have no normal force. If you want to become weightless, have a free fall in an elevator. If you're standing on a scale and you jump off the top of your house, you won't measure any weight because the scale is not pushing back up against you. What is that? Hey folks, this class is going on. Quiet down, please. Well, what if the elevator is moving upwards? Now you have a force that's pushing up. What's going to happen to your weight? Yeah, you gain a few pounds. You gain a few pounds by just standing in an elevator that's going upwards. Put some LBs on. So the normal force is increased, which means your weight's going to increase. Why? Because there is a normal force that's increasing. It's pushing against the scale. What happens to astronauts? They become weightless. Why is that? Yeah, there's no force. Got no force of gravity, very little force of gravity. So your gravitational force is going to be equal to the centripetal force. Basically, you are kept in a circular path. You're kept going around in orbit by the gravitational pull. You just float in a circular path. Every once in a while, you may run into a wall because inertia will make you force you into a wall. Because if the space shuttle, if you're up in a space shuttle or in a spaceship and it starts to turn, your tendency is to go in a straight line path unless acted upon by an unbalanced force. That unbalanced force is the wall or the ceiling or the floor. That's your unbalanced force. So your centripetal force is equal to your gravitational force. (1962), John Glenn was the first American to orbit the Earth in a spaceship called Friendship 7. His maximum height was 262 kilometers, and his minimum height was 160 kilometers. Let's use the average of the two to calculate the orbital period and tangential velocity of Friendship 7. We'll just take the average of those two. Back in 1962, I think they probably had a tough time regulating a lot of things. They were just hoping things didn't go really bad. They had ideas, they had theories, but they were just hoping things didn't go bad. Now there's so many computer space models. They have so much more technology and knowledge that they can run so many simulations on a computer. Okay, they probably had a computer back then and ran some simulations on it, but think about the computer and the simulations back in 1962, or leading into that into the 1950s. What your technology was and what type of simulations that you can actually do, and what type of data do you have to pull from. There's no data. There is literally no data to pull from because nobody has experienced going outside the atmosphere into space travel. It is very similar to having to deal with COVID-19 and what we dealt with for the past year. When you have no data to base everything on, you're not reinventing the wheel, you are inventing the wheel. They're inventing going up in space. They have no model to go by. We had no model to go by with COVID-19 and all the things that we did with COVID-19. We had no model. Yeah, we could go back to 1920 in the Spanish flu. That was somewhat of a model, but back in 1920, people just didn't get up and move and go to this place and this place. When you found a place to live, you pretty much stayed there. You didn't go on vacation all year long. You didn't go hop in an airplane and go on a vacation. You didn't hop in the car and drive down to Florida in an hour or in 15 hours, and all of a sudden you're on vacation. Okay, you didn't have that then. Okay, but they were more sedimentary, which means they were pretty much where they were at. So the average, we'll go with the average height. So if we take a look at the Earth here, we have a circle, and we have Friendship 9 and John Glenn. Circling the orbital path, circling the Earth. And what we'll do, since they have two heights here, 160 kilometers, 262 kilometers, we'll just take the average of those two. I think he was just happy to make it around 3 times without falling back to the Earth. So the distance above the Earth, this distance here, was, let's see, average of that, let's see, that would be 102, so 50, 212, 211, I'm sorry, 211, my bad. So he is 211 kilometers above the Earth's surface. We want to calculate the orbital period and the tangential velocity of Friendship 7. We have the mass of the Earth. Somebody put on the scale the other day. 5.97 times 10 to the 24th kilograms. The radius of the Earth, they got their ruler out. And measured that to be 6.38 times 10 to the 6 kilometers. That's the radius of the Earth. So here's your radius of the Earth. We want to calculate the orbital period and then the tangential velocity. Well, the orbital period from the other side can be calculated by 2 pi r cubed square root of r cubed gm. So we have 2 pi square root of r cubed divided by gm2, which is the mass of the Earth. So we have 2 pi square root, and we have to deal with the radius. What's our radius here? What do we have to do? Ozzy? 6.38. That's the radius of the Earth, but then what else do we have to do with that? Add the 211 kilometers. Okay, so we have problems here. We have kilometers, we have meters. Since we're dealing with G and M, we should probably change them all to meters, because newtons are kilogram meters per second squared. We should put it all into meters. So we have 638,000. I think that's in 6. 1, 2, 3, 4, 5, 6. Okay, that's kilometers. And we have 211. I did that backwards, didn't I? This is meters. There we go, that's a little bit better. Let's change the 211 kilometers into meters. So we have 211,000 meters. So 0, 0, 0, 1, 9, 5, and 6. So on top we have the 6591, 0, 0, 0 to the third power. Then my G value. Oh, what's my G? 6.67 times 10 to the negative 11. And then my mass of the Earth, 5.97 times 10 to the 24th. Now, we're going to get a little KYC activity here. Because we can do that times 10 to the 24th and times 10 to the negative 11. But your calculator is set up for scientific method also. you have a button here. The second button to the comma is an EE button. Okay, you have an EE button. You have a second and the comma. You got the EE button there. What that is, that gives you scientific notation. So if I'm going to multiply these out, I have first one, 6591. So we have 6591000, and that's going to be cubed. So I can take that to the third power. And then we have to divide this by, now we can either quantify and multiply them together, or we can divide it twice. Because remember, your calculator is set up for orders of operations. So if you type in 6.591 cubed divided by 6.67 times 10 to the negative 11th, it's going to divide that out. That value you have to divide by the 5.97 times 10 to the 24th. So you can either divide twice or quantify and multiply. Now, where that EE button helps you out. If I quantify this, I have 6.67. Now that's times 10 to the negative 11th power. So I can go second and EE negative 11 times the 5.97 second EE, whoopsie, second EE to the 24th power, and close your parenthesis out. What it does is basically does your scientific notation for you. Yes, you can type in 6.67 times 10 to the negative 11th power and do that. That is fine. But I'm telling you, the EE button helps you out and saves you having to go to your caret, and then you forget to pull it down out of the caret, and your exponent, and then you have this long exponent there. Then you say some not kind words to your calculator that you hate this calculator. So we have 719,041. Now we have to square root that value. So we have second square root, second answer. Oopsie. Second answer. So we got 8.47 that we multiply by 2 pi. So we multiply times 2 pi. 5,000 or 5,327.9. And that's in seconds. I'm sorry, that's in seconds. Does it make anything different? Everybody get that? Now, once again, if you go to your calculator one more time and I have this, if I do not put my parentheses there, what you have to do then is divide this twice. You take this value and divide it twice. And you'll get the exact same answer that you have to take, hopefully get the same answer. Second square root, second answer. I get the 847, then I can multiply by the 2 pi again. So you can skin the cat one of either way. Okay, we will stop there for today. I guess we can do it. Okay, we'll stop there for today. Calculate the tangential velocity for tomorrow, then we'll worry about problem at the bottom tomorrow also. And we'll see what happens, what engineers have to deal with when they're dealing with vehicles and trying to make sure you're safe going off and on ramp or on and off ramp.